The final layer of the rainforest is not built on size, speed, or spectacle. It is built on precision. By the time the camera settles close enough to resolve individual grains of bark, the scale of the system changes again. The broad logic of territory, trails, and river systems collapses into surfaces, into the skin of the forest itself. A tree trunk becomes a landscape. A single leaf becomes a platform of movement, tension, and exposure. At this level, detection is no longer about interpreting large patterns or responding to spreading signals. It becomes about reading moments. The smallest shifts in posture, the slightest tremor of movement, the faintest trace of chemical presence. This is where the assassin bug operates, and this is where the idea of finding you first becomes almost invisible until it is already complete. The insect does not advertise its presence. It is built to disappear into structure. Its body aligns with the textures of bark, stems, or leaf surfaces, not through perfect mimicry of a single form, but through a general conformity to the irregularity of its environment. Edges are broken, outlines are softened, coloration matches the muted gradients of organic decay or plant tissue. In some species, dust, debris, or even the remains of prey are deliberately accumulated on the body, creating an additional layer of disguise that further disrupts recognition. This is not passive camouflage. It is an active strategy of integration. The assassin bug does not sit on the environment. It becomes part of it. Stillness completes the illusion. Movement is the primary cue for detection among many prey species at this scale. Insects and small arthropods often rely on sudden changes in their visual or vibrational field to trigger escape responses. By remaining motionless, the assassin bug removes itself from that field. It does not need to hide perfectly. It needs only to avoid creating a signal that stands out from the background. This restraint is not temporary. It can persist for long periods, with the insect maintaining a poised, controlled posture that reflects a readiness to act without revealing intent. Positioning is where this strategy gains its effectiveness. The assassin bug does not choose its location randomly. It selects surfaces and orientations that intersect with predictable movement patterns of its prey. The underside of a leaf where small insects feed or rest. The edge of a stem where ants travel in repeated lines. The textured surface of bark where beetles and other arthropods navigate in search of food or shelter. Each of these locations represents a point of convergence, a place where movement is likely to occur not by chance, but by necessity. The insect does not need to track its prey across distance. It needs to occupy the space that prey will eventually cross. At this scale, detection is tied closely to the inevitability of exposure. Prey animals, no matter how cautious, must move to survive. They must feed, mate, reposition, or escape other threats. Each of these actions produces signals, vibrations through the substrate, slight shifts in posture, contact with surfaces that transmit information outward. The assassin bug is tuned to these signals through a combination of sensory systems that operate at close range. Mechanoreceptors detect vibrations and physical contact, while visual cues provide confirmation when movement enters a narrow field of view. Chemical cues, though less dominant, can indicate the presence of prey species or the passage of other insects, adding context to the decision to remain or reposition. The insect's most distinctive feature, the elongated proboscis or rostrum, reflects the precision of its hunting method. This is not a tool for tearing or chewing. It is a piercing instrument designed to penetrate the exoskeleton of prey and deliver saliva that contains a mixture of enzymes and toxins. These substances immobilize and begin the process of external digestion, breaking down tissues into a form that can be ingested. The efficiency of this system depends on timing and placement. The strike must occur when the prey is within reach and in a position that allows for effective penetration. There is little margin for error. A missed strike can alert the prey or even expose the predator to risk. This is where the concept of cue reading becomes central. The assassin bug does not react to every movement in its vicinity. It filters signals, responding only when specific conditions are met. The speed and direction of a passing insect, the angle of approach, the degree of contact with the surface, all of these factors influence the decision to strike. The insect is not processing these variables consciously, but its behavior reflects an evolved sensitivity to patterns that correlate with successful capture. Over time, this results in a highly selective response system that minimizes wasted effort and maximizes efficiency. The moment of action is almost imperceptible. A prey insect moves along a stem, its legs making intermittent contact with the surface, its body aligned with the direction of travel. It is not aware of the presence beside it, because there has been no signal to indicate danger. The assassin bug remains still until the final instant, when the distance closes to a threshold that triggers movement. The strike is rapid, a controlled extension of the forelegs combined with the precise insertion of the rostrum. There is no prolonged chase, no visible escalation. The interaction transitions from absence to contact in a fraction of a second. Once contact is made, the dynamics change completely. The prey's ability to respond is compromised almost immediately, either through mechanical restraint or the rapid effect of the injected saliva. The struggle, if it occurs, is brief and localized. The predator maintains its grip, adjusting its position as needed to ensure control while the process of digestion begins. The event is contained within a space so small that it can occur unnoticed by anything beyond immediate proximity. This is predation reduced to its most efficient form, where detection, action, and consumption are tightly integrated into a single sequence. The ecological implications of this strategy extend beyond individual interactions. Assassin bugs play a role in regulating populations of other insects, influencing the structure of communities at this micro scale. Their presence adds a layer of pressure that shapes behavior, encouraging caution, altering movement patterns, and contributing to the balance of species within the system. This is not a dramatic influence, but a persistent one, operating continuously across countless small interactions that collectively define the dynamics of the forest floor and vegetation. There is also an element of convergence in this strategy when viewed alongside the other hunters of the Amazon. The jaguar reads broad patterns across territory. The bushmaster anchors itself within a corridor of inevitability. The giant otter transforms a river into a shared detection network. The piranha responds instantly to signals delivered through water. The wandering spider actively searches within a dense microenvironment. The assassin bug, in contrast, distills detection to its most minimal form. It does not need to interpret large systems or respond to distributed signals. It needs only to recognize the precise moment when a prey item reveals itself within reach. This progression reveals a unifying principle that runs through the entire system. Detection in the Amazon is not defined by a single method or scale. It is a spectrum, ranging from wide-ranging interpretation to immediate, localized recognition. What connects these strategies is not how they are executed, but what they depend on. The unavoidable fact that every organism produces signals as it moves, feeds, and exists within its environment. These signals vary in form, chemical, mechanical, visual, but they are constant. They cannot be entirely eliminated, only reduced or disguised. The assassin bug demonstrates what happens when a predator is perfectly aligned with this reality. It does not attempt to overcome the complexity of the environment. It simplifies the problem by focusing on the point where complexity resolves into certainty. Prey will move. Prey will make contact. Prey will reveal itself, however briefly, through the act of living. By positioning itself at that point and remaining undetected until the final moment, the assassin bug ensures that the detection event occurs on its terms. This brings the broader idea of the rainforest into sharp focus. Survival is often framed in terms of strength, speed, or aggression, but these traits are only part of the equation. The more fundamental challenge is informational. How much of your presence is visible to others? How much of your movement, your scent, your interaction with the environment becomes a signal that can be read? The answer is never zero. Even the most well-adapted organisms leave traces, create disturbances, and participate in the constant exchange of information that defines the ecosystem. By the time some predators act, the critical moment has already passed. The signal has been produced, the pattern has been recognized, and the position has been set. The strike is not the beginning of the interaction. It is the conclusion of a process that started earlier, often unnoticed. In this sense, finding you first is not always about pursuit or speed. It is about understanding the inevitability of exposure and aligning with it so precisely that action becomes almost unnecessary. The assassin bug closes the narrative not with spectacle, but with clarity. It strips detection down to its essence, revealing a truth that applies across every scale of the Amazon. The forest is not just a place where animals hide and hunt. It is a system where information is constantly generated and interpreted, where survival depends on managing what you reveal as much as how you move. In this system, the smallest predators can be as effective as the largest, not because they dominate physically, but because they understand exactly what they are waiting for, and they wait without being seen until it arrives. The river holds its silence differently than the forest. On land, disturbance settles into place, absorbed by leaf litter and filtered through layers of vegetation. In water, nothing settles in the same way. Motion spreads. A single entry, whether it is the clean slide of a caiman, the awkward stumble of a hoof, or the sudden collapse of a wounded animal, does not remain confined to a point. It radiates outward as pressure, vibration, and chemical diffusion, carried by currents that ignore the boundaries of individual experience. In this medium, privacy is fragile. Information does not need to be sought out across distance. It arrives, diluted but persistent, to anything already within range. This is where piranha fit into the logic of detection, not as relentless hunters of everything that moves, but as highly responsive participants in a system where the right signal travels fast enough to matter. A piranha is not built to patrol vast territory in search of prey. Its strength lies in efficiency within a defined space. Most species form loose schools, not as a constant attack formation, but as a flexible structure that balances risk and opportunity. Within these groups, individuals maintain awareness of each other's position, adjusting spacing and direction in response to subtle cues. This schooling behavior serves multiple purposes. It reduces the likelihood of any one fish being singled out by predators, and it creates a distributed sensory network where information gathered by one individual can quickly influence the movement of others. The group does not need to think collectively in any abstract sense. It simply reacts, each fish adjusting to the signals it receives from both the environment and its neighbors. The river itself provides the first layer of those signals. Water transmits vibration with far greater efficiency than air, and piranha are equipped to detect these disturbances through their lateral line system, a series of sensory organs running along the length of the body that respond to changes in pressure and movement. A struggling fish produces a distinct pattern of vibration, irregular, frantic, and often accompanied by rapid directional changes. This is different from the steady propulsion of a healthy swimmer or the slow drift of debris. The lateral line allows piranha to distinguish these patterns without needing clear visual confirmation, a critical advantage in the often murky waters of the Amazon. Chemical cues form the second layer. Blood is the most widely recognized signal, but it is not unique in its importance. Injury releases a complex mixture of compounds into the water, including alarm substances from damaged tissue that can be detected by other fish. These chemicals diffuse outward, creating a gradient that can be followed or simply recognized as an indicator of vulnerability. However, the effectiveness of these cues depends heavily on context. In a large, fast-moving river, dilution can reduce their impact quickly. In slower, confined waters, oxbow lakes, flooded forests, shallow channels, the same signals can persist longer and remain concentrated enough to trigger a response. This is where environmental conditions begin to shape behavior in meaningful ways. During the dry season, when water levels drop and fish are forced into smaller volumes, density increases and escape options decrease. Under these conditions, the threshold for opportunistic feeding can lower. Competition intensifies, and the cost of ignoring a potential food source rises. In contrast, during the wet season, when the forest floods and resources disperse, piranha are often more widely spread and less likely to respond aggressively to isolated disturbances. The same species in the same river system can exhibit markedly different behavior depending on how space and resources are structured. Understanding this variability is essential to avoiding the common myth of constant frenzy. Piranha are not perpetually on the edge of attack. Much of their time is spent in routine activities, maintaining position within a school, foraging on plant material or small prey, avoiding predators such as caimans and larger fish. Their teeth, sharp and interlocking, are well suited for cutting, but they are tools applied selectively, not indiscriminately. The dramatic feeding events that have captured human imagination are real, but they are conditional. They occur when multiple factors align: a clear signal of vulnerability, a concentration of individuals, and an environment that limits escape. When these conditions do converge, the transition can be rapid. A fish injured near the surface begins to struggle, its movements irregular and increasingly erratic. Vibrations spread outward, intersecting with the sensory fields of nearby piranha. One individual adjusts its path, drawn not by a conscious decision, but by a shift in input, pressure changes, chemical cues, visual flashes of movement. This adjustment is not isolated. Neighboring fish detect the same signals, or they respond to the altered movement of the first. The school begins to reorganize, its structure tightening, its motion becoming more focused. What was previously a loose aggregation becomes a coordinated approach, not through planning, but through the alignment of individual responses to shared stimuli. The first contact is often tentative, a test rather than an immediate escalation. A quick bite, a fragment removed, a confirmation that the signal corresponds to actual food. If the prey continues to struggle, the feedback loop intensifies. More individuals are drawn in, each contributing to the disturbance, each reinforcing the signals that attracted them in the first place. The water becomes increasingly active, not in chaotic frenzy, but in a dense, localized convergence of movement. The event can appear explosive from the outside, but internally it is structured by the same principles that govern the system at all times: detection, response, reinforcement. It is important to recognize that this process does not require long-distance tracking. The piranha are not following a trail across kilometers of river. They are responding to information that has already arrived within their immediate environment. The river has done the work of distribution, carrying signals outward until they intersect with receptive individuals. In this sense, the idea of finding you first becomes less about pursuit and more about proximity. If the right signal reaches the right density of fish under the right conditions, the response is almost immediate. There is no delay for search, no need for extended interpretation. The system is already in place, waiting for input. This dynamic extends beyond feeding. Piranha are also sensitive to changes in their own risk environment. Sudden disturbances that do not correspond to prey, large, steady displacements of water, unfamiliar shapes or patterns associated with predators can trigger avoidance behavior. The same lateral line and chemical detection systems that draw them toward opportunity can also push them away from danger. This dual sensitivity reinforces the idea that their behavior is not driven by indiscriminate aggression, but by a continuous assessment of cost and benefit. Feeding events occur when the balance shifts decisively in favor of reward. The structure of the school enhances this responsiveness. Information does not need to pass through a hierarchy. Each fish processes local input and adjusts accordingly, but because individuals are closely spaced, these adjustments propagate quickly through the group. A change in direction by a few fish can influence the movement of many, creating a cascading effect that appears coordinated at the group level. This is not cooperation in the human sense, but it produces a functional equivalent. The school acts as a distributed sensor with multiple points of contact with the environment, increasing the likelihood that relevant signals are detected and acted upon. There is a certain economy to this system. Piranha do not expend energy searching widely for rare opportunities. They occupy environments where information is likely to arrive and rely on their sensitivity to detect it when it does. This aligns with broader patterns in the Amazon, where many species are adapted not to constant pursuit, but to strategic positioning within flows of resources and signals. The river is not just a habitat. It is a conveyor of information, and species that can interpret that information efficiently gain a significant advantage. For an animal entering this environment, the implications are subtle but significant. The initial act, stepping into the water, wading across a channel, or struggling after injury, may seem localized. But in a medium where movement and chemistry spread rapidly, that act is immediately translated into signals that extend beyond the point of origin. The individual may not perceive this expansion. It feels contained, personal, and momentary. Yet within seconds, it can intersect with the sensory fields of multiple fish, each capable of responding in ways that reinforce the initial disturbance. This is where the fear becomes grounded, and precise. It is not that piranha are everywhere waiting for any excuse to attack. It is that under the right conditions, they do not need to be far away. They need only to be present within the reach of a signal that travels efficiently through their environment. When that signal is clear, when it carries the combined information of vulnerability, movement, and opportunity, the response can unfold quickly, not because of uncontrolled frenzy, but because the system is designed to convert information into action with minimal delay. In the broader narrative of the rainforest, this chapter sharpens the idea of detection by stripping it down to its essentials. There is no need for long-term tracking, no requirement for complex interpretation across large distances. The river does not ask its inhabitants to search widely. It delivers what matters, when it matters, to those positioned to receive it. The piranha are not the authors of this system. They are its most immediate responders, turning a fleeting signal into a tangible event. In doing so, they reveal a different truth about the Amazon. Sometimes the danger is not in being followed, but in being noticed all at once. The rainforest does not begin with sight. It begins with residue. Before a shape moves between the trees, before a sound breaks the layered hum of insects and distant birds, the forest is already holding a record of everything that has passed through it. Moist air traps sent close to the ground, leaf litter preserves pressure marks, and every contact, every step, every brush of fur against bark, every drop of sweat or blood, adds another line to a constantly rewritten map. In this environment, movement is never anonymous. It is translated, stored, and made available to anything capable of reading it. At the top of that sensory hierarchy moves the jaguar, a predator that does not simply travel through the forest, but interprets it in real time. A jaguar's presence is rarely announced visually. It exists first as a pattern of decisions. Trails that are used repeatedly by prey, narrow paths pressed into the soil by hooves or paws, become predictable corridors of information. Riverbanks, fallen logs, and root systems act as crossing points where animals funnel their movement, compressing the randomness of the forest into moments of inevitability. A tapir entering water at the same bend each evening, a peccary herd circling a fruiting tree, a capybara returning to a mud wallow. These are not isolated events. They are routines, and routines are the foundation of detection. The jaguar does not need to search blindly. It positions itself within these patterns, allowing the forest to bring information to it. Scent is the dominant layer of this system, but it is not a single signal. It is a composite of overlapping chemical messages that carry different types of information. Urine marks left by mammals contain indicators of sex, reproductive status, and individual identity. Gland secretions deposited on trees or ground surfaces reinforce territorial boundaries and social presence. Sweat carries stress hormones that can spike during flight or injury, subtly altering the chemical profile of a moving animal. Even disturbed vegetation releases volatile compounds when crushed or broken, creating a transient but readable trace of passage. In the humid stability of the Amazon, these signals persist longer than they would in drier systems, forming a dense, layered archive. The jaguar's olfactory system is built to pass this complexity. Its nasal cavity contains an intricate network of turbinate bones that increase surface area for scent detection, allowing airborne molecules to be sampled with high resolution. The vomeronasal organ, located in the roof of the mouth, processes heavier, non-volatile compounds, those often associated with pheromones and close contact chemical signals. When a jaguar pauses and curls its lip in a flamen response, it is not displaying aggression, but actively analyzing this deeper layer of scent information. What appears to be a moment of stillness is, in reality, a rapid assessment. How recently an animal passed, whether it was stressed, whether it is alone or part of a group, and whether it is likely to return. This ability transforms the forest from a visually obstructed environment into a chemically transparent one. Dense foliage that blocks sight does not block scent. A prey animal moving through undergrowth may feel concealed, but concealment in the Amazon is only partial. Each step compresses soil, releases odor, and leaves microscopic traces that accumulate into a detectable path. Even water, often assumed to erase tracks, does not fully eliminate this signature. Entry and exit points at riverbanks create concentrated zones of disturbance where scent, mud displacement, and broken vegetation converge. Jaguars frequently patrol these interfaces, not because they can see prey easily there, but because prey is forced to reveal itself more completely when transitioning between mediums. Movement patterns amplify this vulnerability. Many rainforest animals rely on efficiency to conserve energy, especially in a system where resources can be patchy and competition is constant. This efficiency often manifests as repeated use of the same routes. Over time, these routes become predictable, not just spatially, but temporally. A jaguar does not need to memorize individual animals. It learns the rhythm of the landscape. The forest becomes a schedule written in scent and disturbance, where certain places become more informative at certain times of day. Twilight, when many species transition between rest and activity, is particularly dense with overlapping signals. For a predator capable of interpreting them, this is not chaos, but opportunity. The jaguar's body plan complements this sensory advantage. Its movement is controlled, economical, and deliberate, minimizing the amount of new disturbance it creates while navigating existing trails. Unlike cursorial predators that rely on long chases, the jaguar is an ambush specialist. Its muscular build allows for explosive power over short distances, but that power is only deployed after a period of information gathering. Each step is placed to maintain silence and reduce unnecessary scent deposition, effectively allowing the jaguar to move within the chemical map without overly rewriting it. This restraint is critical. In a system where detection works both ways, excessive disturbance can alert prey as easily as it reveals it. Prey species, in turn, have evolved countermeasures, but these are often imperfect. Many animals engage in scent marking of their own, which can create confusion or mask individual identity within a group. Herding behavior dilutes the signal of any single animal, making it harder to isolate a target. Some species vary their routes or timing to reduce predictability. However, these strategies are constrained by ecological needs. Access to water, food, and shelter often forces animals back into the same key areas, reintroducing patterns that a jaguar can exploit. Avoidance is possible, but it is rarely absolute. What makes the jaguar particularly effective is not just its ability to detect, but its ability to prioritize. The forest contains an overwhelming amount of information, and not all of it is relevant. A fallen branch disturbed by a monkey hours ago carries a different significance than fresh tracks leading to water. The jaguar filters these signals, focusing on those that indicate recent, repeatable, or high-value movement. This selective attention reduces noise and sharpens the predator's response, allowing it to act decisively when the right conditions align. Blood introduces another layer to this system, but it is not the primary driver. Contrary to popular imagination, jaguars do not roam the forest following blood trails like exaggerated hunters from fiction. Blood is a strong signal, but it is also rare and often short-lived. Its importance lies in its context. When combined with signs of struggle, disturbed ground, broken vegetation, stress-related scent compounds, it can indicate vulnerability. A wounded animal is not just easier to catch, it is more predictable in its movement, often retreating to water or cover in ways that can be anticipated. The jaguar reads this combination of signals as a shift in opportunity, adjusting its behavior accordingly. The result is a predator that does not rely on a single sense or tactic, but on the integration of multiple information streams. Vision, hearing, and scent all contribute, but scent provides the continuity that ties them together. It allows the jaguar to track not just where an animal is, but where it has been and where it is likely to go. This temporal dimension is what makes detection in the Amazon so effective. The forest is not just a snapshot of the present, it is a layered record of recent history, and the jaguar is one of its most skilled readers. For anything moving through this environment, without that level of sensitivity, the experience is fundamentally different. The forest appears dense, chaotic, and partially obscured. Movement feels anonymous, and the absence of visible predators can create a false sense of security. But this perception is incomplete. Each action, each step, each pause, each decision to follow a familiar path adds to a growing body of information that is accessible to those capable of interpreting it. The jaguar does not need to be seen to be effective. It needs only to understand. This is what makes it the perfect opening to the idea of detection in the rainforest. The danger is not limited to the moment of attack, nor is it defined solely by physical strength. It begins much earlier at the level of information. The forest is constantly being written by the animals that move through it, and the jaguar is one of the few that can read that writing with precision. In this system, survival is not just about speed or strength, but about how much of yourself you reveal without realizing it. The forest floor is where the illusion of randomness breaks down. From above, the Amazon appears chaotic, an uninterrupted mass of green layered over shadow, but at ground level, movement is guided, constrained, and quietly organized by structure. Roots rise and twist through the soil, fallen branches create barriers, and dense vegetation funnels animals into narrow corridors where passage becomes easier, safer, or simply unavoidable. Over time, these routes are reinforced not only by physical wear, but by repetition. Rodents follow them. Small marsupials follow them. Ground foraging birds cross them. Even larger animals, when forced to navigate dense understory, intersect them at predictable points. The result is not a single trail, but a network of pathways shaped by necessity. In this network, the bushmaster does not wander. It selects. Unlike a jaguar, which interprets a broad field of sensory information across a large territory, the bushmaster operates with precision anchored to place. It does not need to read the entire forest. It needs to understand one section of it completely. This distinction is critical because it reframes detection as something far quieter and far more controlled. The bushmaster is not searching for prey in the active sense. It is positioning itself where prey will inevitably pass. The intelligence lies not in pursuit, but in choosing the right ground that has already been pre-selected by the behavior of other animals. Leaf litter becomes the primary medium of this system. It is not just a covering, but a record of disturbance. Each step compresses it, shifts it, rearranges its layers. Small mammals leave faint but consistent impressions as they move between feeding sites and shelter. Their bodies brush against low vegetation, depositing scent and altering the arrangement of leaves in ways that persist for hours or days, depending on humidity and rainfall. The bushmaster does not need to interpret these signals with the same resolution as a mammalian predator. It benefits from their accumulation. Where disturbance is frequent, traffic is high. Where traffic is high, opportunity concentrates. The snake's body reflects this strategy. Heavy, muscular, and built for ambush rather than speed, the bushmaster cannot afford inefficiency. Movement is costly, both in energy and in exposure. Every relocation risks detection, and every unnecessary shift reduces the advantage of stillness. As a result, its behavior emphasizes site fidelity, remaining in a chosen position for extended periods when conditions are favorable. This is not passivity. It is an investment. The longer the snake remains undetected in a high-traffic corridor, the more likely it is that prey will intersect with its position. Thermal and sensory adaptations support this approach. The bushmaster's heat-sensitive pit organs allow it to detect infrared radiation, effectively seeing the body heat of warm-blooded animals even in low-light conditions or partial cover. This does not function as a wide-ranging search tool. It is a close-range system optimized for the final moments before a strike. Combined with its ability to remain motionless for long periods, it creates a detection zone that is invisible to prey until it is too late. The snake does not need to track an animal's entire path. It needs only to recognize when that path has entered its immediate range. Chemical cues still play a role, but again, not in the dramatic sense often imagined. The forked tongue samples airborne particles, transferring them to the Jacobson's organ for analysis. This allows the bushmaster to detect the presence of prey species and assess general activity levels in its surroundings. However, this system is not used to follow trails over long distances. It is used to confirm that the chosen location remains relevant, that the corridor is still active, that prey is still moving through it. If the chemical environment changes significantly, the snake may relocate. But as long as the signals remain consistent, it holds its position. The effectiveness of this strategy becomes clear when considering the behavior of the animals that create these pathways. Small mammals, in particular, are creatures of habit. Their survival depends on efficiency and familiarity. Repeated routes reduce the cognitive load of navigation and minimize exposure to unknown threats. Over time, these routes become deeply embedded in their behavior, to the point where deviation is rare unless forced by external factors. This predictability is what the bushmaster exploits. It does not need to anticipate every possible movement. It only needs to occupy the movements that happen most often. Environmental conditions amplify this effect. In the humid, stable climate of the Amazon, scent and physical disturbance persist longer than in more variable systems. Rainfall can reset the surface, but between storms, the forest floor accumulates information. The density of vegetation further restricts movement, reinforcing the use of established corridors. Even seasonal changes, such as fruiting cycles or fluctuations in water levels, tend to concentrate activity rather than disperse it. Animals adjust their routes to follow resources, but in doing so, they often converge on the same limited set of viable paths. For an ambush predator, this convergence is not a challenge. It is an advantage. The bushmaster's coloration and texture complete the system. Its body blends seamlessly with the leaf litter, not through perfect mimicry of any single element, but through a composite resemblance to the forest floor as a whole. Patterns of brown, tan and shadow break up its outline, while the irregular shapes of leaves and debris obscure its form. This camouflage is not static. It works in conjunction with stillness. Even slight movement can reveal the snake's presence, but when motionless, it becomes part of the background, indistinguishable from the environment it inhabits. Prey animals, scanning for movement and contrast, often fail to detect it entirely. Strike mechanics reflect the same principle of efficiency. When prey enters range, the Bushmaster delivers a rapid, precise bite, injecting venom designed to disrupt the victim's physiology quickly. The goal is not prolonged pursuit, but immediate incapacitation or, at minimum, a significant reduction in the prey's ability to escape. In many cases, the snake will release the prey after striking, allowing the venom to take effect while minimizing the risk of injury from struggling. It then tracks the envenomated animal over a short distance, guided by chemical cues, until it can safely consume it. Even here, the strategy remains conservative, focused on reducing risk rather than maximizing speed. This approach highlights a broader principle of detection in the rainforest. It is not always about finding an animal actively. It is about being found by the patterns that animal cannot avoid. The Bushmaster does not need to interpret the entire chemical map of the forest. It relies on the fact that other animals have already simplified that map through their behavior. By repeatedly using the same routes, by concentrating their movement in predictable areas, they create zones of inevitability. The snake positions itself within one of these zones and waits for the system to deliver. There is a subtle irony in this dynamic. The same behaviors that help prey survive in a complex environment, efficiency, familiarity, route optimization, also make them vulnerable to a predator that understands those behaviors. The forest does not reward randomness indefinitely. Over time, patterns emerge, and those patterns can be exploited. The Bushmaster is not an anomaly within this system. It is a product of it, shaped by the same constraints and opportunities that influence every other organism in the ecosystem. For an observer moving through the rainforest, this reality is difficult to perceive. The ground appears uneven but unstructured, the leaf litter a uniform layer of debris. Without knowledge of the underlying patterns, it is easy to assume that movement is arbitrary. But at the scale that matters to the Bushmaster, the forest floor is organized. It is a network of pathways defined by use, reinforced by necessity, and constantly updated by the animals that traverse it. The snake does not need to reveal itself to interact with this network. It becomes part of it, an unseen node where movement and opportunity intersect. This is what makes the Bushmaster's presence feel colder and more silent than that of a pursuing predator. There is no chase, no visible tracking, no gradual closing of distance. The interaction is defined by stillness and timing. The animal does not find the snake through a series of escalating cues. It encounters it at the exact moment when avoidance is no longer possible. Detection, in this context, is not something that happens before the encounter. It is something that has already happened long before in the repeated choices that led the prey to that specific piece of ground. In the broader logic of the rainforest, this represents a different kind of intelligence. It is not the wide-ranging interpretation of a jaguar reading the forest as a dynamic, shifting document. It is a focused mastery of a single paragraph within that document, understood so completely that nothing passing through it goes unnoticed. The Bushmaster does not need to know everything. It needs to know enough in the right place at the right time. And in a system built on repetition and necessity, that is often more than sufficient. Night in the Amazon does not simply reduce visibility, it redistributes attention. The canopy, which dominates perception during the day, dissolves into a layered darkness where the ground begins to take precedence. Moisture settles, temperatures soften, and a different set of movements emerges, smaller, closer, and more numerous. Leaf litter shifts with subtle activity. Insects move through narrow tunnels between debris. Amphibians reposition in search of humidity gradients. The forest floor becomes a network of microhabitats, each defined by slight differences in moisture, temperature, and cover. It is within this scale that the Brazilian wandering spider operates, not as a passive occupant of a fixed site, but as an active searcher moving through a constantly changing landscape. Unlike ambush predators that rely on the predictability of pathways, the wandering spider embraces variability. Its strategy depends on motion, controlled, deliberate, and continuous. The body remains low to the ground, legs extended to maximize contact with the substrate, each step placed with a precision that reflects both caution and intent. This is not aimless wandering. It is structured exploration, guided by a combination of tactile, chemical, and vibrational cues that reveal the presence of prey in environments where direct visibility is limited. The spider does not need to see its prey clearly. It needs to detect the disturbances that prey cannot avoid creating. The forest floor at this scale is not silent. It is saturated with micro-vibrations produced by the movement of countless organisms. An insect navigating through leaf litter generates a distinct pattern of contact, irregular, intermittent, and often constrained by the structure of its environment. A small frog shifting position produces a heavier, more deliberate disturbance, with pauses that reflect its stop-and-go movement. Even the act of breathing or slight repositioning can transmit faint signals through the substrate. The wandering spider is equipped to interpret these cues through highly sensitive mechanoreceptors located on its legs. These receptors detect minute changes in pressure and vibration, allowing the spider to localize activity without relying on sight. This sensory system is complemented by a level of mobility that is unusual among spiders of its size. Rather than constructing a web and waiting for prey to become entangled, the wandering spider actively traverses its environment, moving between microhabitats that concentrate activity. The base of a tree, where roots create pockets of shelter and humidity, becomes a focal point. The underside of a fallen log, where insects gather to feed on decaying material, offers another. The edges of small clearings, where temperature gradients shift and prey species adjust their behavior accordingly, provide additional opportunities. Each of these locations is not chosen randomly, but because it represents a convergence of conditions that increase the likelihood of encountering prey. Chemical cues add another layer to this process. While the wandering spider does not track scent over long distances in the way a mammalian predator might, it is capable of detecting localized chemical signals that indicate recent activity. Silk threads left by other arthropods, pheromones released during mating, or the residual scent of prey species can all inform the spider's movement. These cues do not create a continuous trail to follow. Instead, they function as indicators of probability, guiding the spider toward areas where prey is more likely to be present. In a system where energy must be balanced against opportunity, this selective movement increases efficiency without requiring long-range tracking. The spider's vision, though not its primary sense, contributes to this close-range detection. Its eyes are adapted for low-light conditions, capable of distinguishing movement and contrast within the immediate environment. This allows the spider to confirm the presence of prey once it has been localized through vibration or chemical cues. The integration of these sensory inputs, vibration, chemistry and vision, creates a layered detection system that operates effectively within the confined spaces of the forest floor. What distinguishes the wandering spider within the broader context of the rainforest is the intimacy of its hunting range. While larger predators operate across territories measured in kilometers, this spider functions within centimeters. The difference is not just scale, but perspective. At this level, the environment is dense with potential interactions. A single square meter of leaf litter can contain dozens of organisms, each contributing to a complex web of signals. For the spider, this density is not overwhelming. It is exploitable. The challenge is not finding prey in a vast space, but isolating the relevant signals within a crowded one. This is where behavior becomes critical. The wandering spider does not move continuously at a uniform pace. It alternates between motion and stillness, pausing to sample the environment before advancing again. These pauses are not passive. They allow the spider to refine its perception, filtering out background noise and focusing on specific disturbances. A slight shift in vibration, a change in chemical intensity, or a brief visual cue can trigger a directional adjustment. Over time, these incremental decisions guide the spider toward its target, not through direct pursuit, but through a series of informed movements that reduce uncertainty. Prey species, in turn, are adapted to this environment in ways that reflect constant pressure from such predators. Many insects rely on camouflage, blending into the textures and colors of the leaf litter to avoid detection. Others minimize movement, remaining still for extended periods to reduce vibrational signals. Some exploit vertical space, climbing onto vegetation to escape ground-based threats. However, these strategies are not foolproof. The same conditions that provide cover also constrain movement, forcing prey into predictable behaviors that can be recognized and exploited. The wandering spider does not need to overcome every defense. It needs only to exploit the moments when those defenses are compromised. The interaction, when it occurs, is rapid and decisive. Once prey is within reach, the spider closes the distance with a sudden acceleration, delivering a bite that introduces venom designed to immobilize. The venom's composition varies among species, but in the Brazilian wandering spider, it is potent enough to disrupt neural and muscular function quickly in small prey. This ensures that the struggle is brief, reducing the risk of injury to the spider and preventing the prey from escaping into the complex structure of the forest floor. The event is localized, almost invisible at a distance, yet it represents the culmination of a detection process that has been unfolding over several seconds or minutes. There is an inherent contrast between this mode of detection and the broader patterns seen in larger predators. The jaguar reads the forest as a wide, interconnected system, interpreting signals across distance and time. The bushmaster anchors itself within a specific corridor, allowing patterns of movement to converge on its position. The giant otter transforms a stretch of river into a collectively monitored space. The piranha responds to signals that arrive through the medium of water. The wandering spider, by comparison, compresses detection into the immediate present. It does not rely on the accumulation of information over large scales. It operates within a constantly shifting microenvironment where detection and response are tightly coupled. This compression creates a different kind of vulnerability for anything moving through the forest. The assumption that danger comes from large, visible animals overlooks the density of smaller predators operating at close range. Each step through leaf litter, each contact with bark or root, places an organism within the detection field of hunters that are actively searching, not waiting. The proximity is what makes this dynamic unsettling. There is no buffer of distance, no gradual escalation of cues. The interaction occurs within a space that is often measured in centimeters, where detection can transition to contact almost instantly. Environmental conditions further influence this process. Humidity affects the transmission of chemical cues and the behavior of prey species, often increasing activity during periods of higher moisture. Temperature gradients can shift the distribution of insects and other small animals, concentrating them in specific areas that the spider learns to exploit. Even subtle changes in light, such as the presence of moonlight filtering through the canopy, can alter movement patterns, creating windows of increased opportunity. The wandering spider is not responding to these factors in a conscious sense, but its behavior is shaped by them, aligning its activity with the conditions that maximize success. In this context, the forest floor becomes a dynamic detection zone, where multiple layers of information are constantly being generated and interpreted. The wandering spider is one of many participants in this system, but its active searching behavior makes it particularly effective. It does not depend on chance encounters. It creates them, moving through the environment in a way that increases the likelihood of intersecting with prey. This is not randomness. It is a form of structured exploration that leverages the density and complexity of the ecosystem. What this chapter ultimately reveals is that detection in the Amazon is not confined to scale or spectacle. It operates at every level, from the broad territories of large predators to the intimate spaces of the forest floor. The wandering spider embodies this principle by bringing the concept of being found into immediate proximity. It reminds us that the rainforest is not only a place where large animals track and ambush, but also a place where smaller hunters are constantly searching, their presence felt not through dramatic encounters, but through the quiet efficiency of their movements. In the layered reality of this ecosystem, the idea of safety becomes relative. Avoiding the attention of a jaguar does not remove an organism from the web of detection. It simply shifts the scale at which that detection occurs. The wandering spider operates within that smaller scale, where the distance between observer and observed is minimal, and where the boundary between movement and contact is thin. It is a reminder that in the Amazon, being unnoticed is not a fixed state. It is a temporary condition, maintained only as long as the signals you produce remain indistinguishable from the background. The river does not hide information the way the forest floor does. It transforms it. Movement in water spreads, stretches, and amplifies into patterns that travel far beyond the point of origin. A fish breaking formation, a body displacing the surface, a sudden burst of speed beneath the shallows. These events do not remain local. They ripple outward, intersecting with currents, reflecting off banks and carrying signals downstream. In the Amazon, where visibility is often limited by tannins, suspended sediment and shadow, the river becomes a medium of transmission rather than concealment. It is not a place where intrusion disappears. It is a place where intrusion announces itself in motion. Within this system, the giant otter operates not as an isolated hunter, but as part of a coordinated network that reads these signals collectively. A stretch of river occupied by giant otters is not simply used. It is structured. Banks become boundaries, sandbars become checkpoints, and specific locations accumulate meaning through repeated activity. Latrines, communal sites where the group deposits feces and scent, function as anchors of territorial identity. These are not random waste areas, but deliberately chosen points that maximize signal persistence and visibility. Positioned on exposed banks or near frequently used channels, they create concentrated zones of chemical information that define ownership. The scent carried in these deposits is complex, containing markers of group identity, reproductive status, and individual presence. For an otter group, these sites are not just markers left behind. They are continuously updated declarations, refreshed and reinforced through routine visits. Between these fixed points, movement patterns form a living mesh of surveillance. Giant otters patrol their territory not in rigid lines, but in overlapping circuits that keep multiple individuals in motion across the same general area. This creates redundancy. If one otter misses a signal, another is likely to encounter it shortly after. The group does not rely on a single detection event. It relies on accumulation and confirmation. This is where the social dimension becomes decisive. Information does not remain with the individual that detects it. It is shared, reinforced, and acted upon collectively. Vocal communication plays a central role in this process. Giant otters are among the most vocal of the mustelids, producing a wide range of sounds that carry across water with clarity. These are not random calls, but structured signals that convey urgency, location, and context. A sharp alarm bark can alert distant group members to the presence of an intruder, while softer contact calls maintain cohesion during routine movement. The river surface acts as an acoustic amplifier, allowing sound to travel efficiently over long distances. In a system where visibility is often obstructed, this auditory layer ensures that detection is not confined to line of sight. Physical disturbance adds another dimension. Unlike the forest, where movement can be partially absorbed by vegetation, water records motion in continuous, visible form. A swimming animal leaves a wake, a signature shaped by its size, speed, and direction. Giant otters are highly attuned to these patterns. A familiar group member produces a predictable disturbance, rhythmic, consistent, and aligned with known behavior. An unfamiliar presence disrupts this pattern. A sudden, erratic wake, a body moving against the typical flow of activity, or a surface break in an unexpected location can all trigger attention. These cues do not need to be interpreted in isolation. They are cross-referenced with scent, sound, and prior knowledge of the territory. Feeding activity further sharpens this system. Giant otters are active predators, often hunting fish in coordinated bursts that generate intense, localized disturbance. Schools of fish scatter, water churns, and the surface becomes briefly chaotic. Within this chaos, patterns still exist. The group knows its own hunting signatures, the timing, the spacing, the rhythm of splashes. When a similar disturbance occurs outside of these expected patterns, it stands out. A fish thrashing alone near the surface, a sudden burst of prey movement without the accompanying signals of a hunting group, or the presence of blood in the water, can all indicate an anomaly. In a territory that is constantly monitored, anomalies are rarely ignored. The concept of belonging becomes critical here. Every individual within a giant otter group contributes to and reinforces a shared environmental baseline. Familiar scents, familiar sounds, familiar movement patterns, all of these define what is normal within that stretch of river. Anything that deviates from this baseline becomes immediately conspicuous. This is not detection in the sense of actively searching for a specific target. It is detection through contrast. The system is tuned so precisely to its own regularity that irregularity becomes a signal in itself. Den sites intensify this sensitivity. Located along riverbanks, often concealed within root systems or burrows, these areas represent points of high vulnerability. Young otters, limited in mobility and experience, depend on the group for protection. As a result, the area surrounding a den is subject to heightened scrutiny. Movement slows, vigilance increases, and the threshold for responding to unusual stimuli drops. An unfamiliar scent near the entrance, a disturbance in the waterline, or even a subtle change in the acoustic environment can trigger a coordinated response. In these zones, detection is not just about identifying prey or competitors. It is about maintaining the integrity of the group itself. The sensory capabilities of giant otters support this layered awareness. Their eyesight is well adapted for both above and below water, allowing them to track movement across different mediums. Their whiskers, or vibrissae, are highly sensitive to water displacement, detecting minute changes in flow and pressure. This tactile sense is particularly effective in low visibility conditions where visual cues are limited. Combined with acute hearing and a functional sense of smell, these adaptations create a multi-channel detection system that operates continuously. Each sense contributes a piece of information, and together they form a coherent picture of the environment. Thermoregulation and physiology also influence behavior in ways that reinforce detection. Giant otters, with their dense fur and high metabolic rate, must remain active to maintain body temperature in water that can draw heat away efficiently. This constant movement is not just a necessity of survival. It becomes a mechanism of surveillance. As individuals move through the territory to forage, groom, and interact, they simultaneously sample the environment. The need to stay warm ensures that the system remains active, reducing the likelihood of gaps in coverage. Social structure amplifies all of these factors. A typical giant otter group consists of a breeding pair and their offspring, forming a cohesive unit that shares responsibilities. Younger members learn through participation, gradually integrating into the detection network. This creates continuity across generations. Knowledge of the territory, its boundaries, its key locations, its typical patterns, is not static. It is maintained and transmitted through behavior. The river is not just a physical space. It is a learned environment, understood collectively and reinforced over time. This collective intelligence changes the nature of intrusion. An individual entering a giant otter's territory does not encounter a single observer. It encounters a system. The first signal, an unfamiliar scent, an unusual wake, a misplaced sound, may be detected by one otter. But that detection does not remain isolated. It is communicated, confirmed, and acted upon by the group. Response can be rapid and coordinated, with multiple individuals converging on the source of disturbance. This is particularly evident in defensive situations where giant otters have been observed confronting larger predators, including caimans, through collective aggression and intimidation. The efficiency of this system lies in its redundancy. No single point of failure can collapse it. If visibility is poor, sound compensates. If scent is diluted by current, movement patterns remain. If one individual is absent, others continue the patrol. The river, in this context, becomes a shared sensory field, continuously read and updated by multiple participants. Detection is not a moment. It is a process distributed across space and time. There is a certain inevitability to this arrangement. A stretch of river occupied by giant otters cannot remain neutral for long. It becomes defined by their presence, structured by their behavior, and saturated with their signals. Anything entering that space is immediately subject to comparison against this established baseline. It is not simply a matter of being seen or heard. It is a matter of fitting or failing to fit within a system that is already in motion. This is where the idea of finding you first takes on a different meaning. It is not about speed or singular perception. It is about coverage. A lone predator may miss a cue, overlook a signal, or arrive too late. A group operating as a network reduces these uncertainties. Information is gathered from multiple angles at multiple times and integrated into a shared response. The river does not need to be searched completely at any given moment. It is effectively always being searched in parts, with those parts overlapping enough to create continuity. In the end, the giant otter transforms detection from an individual act into a collective property of the environment. The river becomes readable not because one animal is exceptionally skilled, but because many animals are contributing to the same interpretive process. For anything moving through that water, this creates a different kind of exposure. It is not the sudden realization of a hidden predator, nor the silent intersection with an unseen ambush. It is the gradual, often imperceptible recognition that the environment itself is aware and that awareness is shared.